In the cut and paste activity that we did the other day, I talked to you guys a little bit about concavity, and where you had to know what the inflection point was. And those of you that are from regular pre-cal, you talked about concavity, and if you were from honors pre-cal, probably not so much. At least that's from what I gathered from you guys. So I want to talk a little bit about this idea of concave up and concave down, and then we'll jump over to the notes. So you don't need to really write anything here. I just want to talk a little bit about it and what it is. Now, the shape of concave up is pretty recognizable. Basically, if you have this U shape right here, that's concave up, and then if you have, the upside down U, that's concave down. So that's the shape, so it's pretty recognizable. You can look at a graph and oh, right there it's concave up, right there it's concave down. But as far as what's going on in terms of derivatives and slopes and things like that, what it means is a graph is said to be concave up anywhere that the slopes are increasing. I talked to you guys about this, in the last chapter, how there's a difference between saying f prime is positive and saying f prime is increasing. Those two things mean different things. What I mean by that is when a graph is concave up, like this red graph right here, then think about what the slope would be way off on the left. All right, this real steep tangent line, this would be a really big negative number right there. And as you move along from left to right, right here, the slope is still negative, but a little less negative. And then down here, the slope is 0, and then a small positive number, and then right here, you get a pretty big positive number. And so what's happening is from left to right, the slopes are increasing. All right? So if you notice here in this little region, here the slopes are all positive, but they're also increasing. So there is a difference between the slopes being positive and increasing. Like for instance, in this section over here, the slopes are negative, but they're still increasing. They're getting bigger. Like if I throw numbers to this slope would be like -10 right here. And then this slope here would be like -2. So it's growing. Even though it's negative, it's still growing. So that's what it means to be concave up. F prime is increasing. And then if you look over on the other side, here it's a pretty big positive number, the slope. And then right here, it's positive, but small positive. Here is 0. And then a little negative. And then way over here, a big negative. So you could see that f prime, or the slopes, are decreasing. That's what it means to be concave down. Okay? All right, so we're going to jump over to the actual note sheet. All right. So far, we've talked a lot about the first derivative. That's what the entire chapter 2 is about. That's what the first half of this chapter has been about. And the first derivative tells you all about where the original function is increasing or decreasing. Increasing or decreasing. That's what the f prime does, if you will. That's what the first derivative does, is it tells you where the original function is increasing and decreasing, and then that indirectly leads into relative max and relative mins. Today's lesson is all about the second derivative, f double prime. The second derivative is all about concavity. The second derivative is all about concavity of the original function. All right. So f prime tells you where a function is increasing or decreasing. F double prime tells you where a function is concave up or concave down. Okay. So if you look here, the graph of f is given, and it says sketch f prime and f double prime. And we've worked a lot on this, so hopefully we could do this fairly well. So I'm going to do f prime in red. And what I like to do is I like to identify anywhere the slope is 0. So like right here. So on the x-axis is where f prime will be. Up here at this relative maximum has a slope of 0, so f prime will cross the x-axis right there, has a slope of 0. And so now you just have to get an idea of some test points along the way. Like if I look over here, I know the slope is a big negative number. So on the f prime graph, the red graph, where that point is at that x value, I just go down here somewhere. I don't know exactly what the number is, but I know it's a pretty big negative. I'm looking for another stylus pen because this one's not working so well, but I can't find one. All right, and so we're starting here, we're coming up, And then we notice that the slopes now start to become positive in this range. They start to become positive until they get to this point right here, and that is where the slope is the most positive. So at that x value, I put, and I don't know exactly what the slope is, but I know at that x value, it's going to be the biggest positive. So right there. And then we come down. And then on this side right here to the right of this point up here, the graph starts to decrease, so it goes into the negative range. And this slope down at the end is a big negative, something way down here. Which makes sense. The original graph is a cubic function, so we should get some sort of parabola, if you will. So that's f prime, and we've worked on that a decent amount. Well, now I want to do f double prime. Okay, so I'll do f double prime in blue. So we do the same thing, just with the red graph now. So again, if I want f double prime, now I want to find the derivative of the red graph. So anywhere that there's a horizontal tangent, so right here, at that relative max of the red graph, I could put on the x-axis. To the left of that point, think about what's going on over here in this range. The slopes are all positive. Way down here, actually, it's the biggest positive. So on the f double prime graph, there's going to be some slope up here. I don't know what it is, but it's a big positive. And then as you go from left to right, you start to come to that x-intercept. And then on the other side of this relative max here, it starts to decrease. So we get into the negative range right there. Okay. And we've practiced a lot with that, so hopefully that made sense. Try to clean this up a little bit. Okay, so blue is f double prime. Red is f prime. All right, now I want you to look, okay? On the original function, right here, the graph is concave up, where I just highlighted. Look at f double prime over that interval. Look at f double prime, all these blues, if you will. All those blues are above the x-axis. So where that purple is highlighted, where the graph is concave up, f double prime is all above the x-axis. So just like if you look at f prime, where f prime is positive, the original function's increasing. Well, where f double prime is positive, the original function is concave up. And that's how we can determine concavity. We're looking at the second derivative, and if f double prime is greater than 0, then f of x is concave up. I hate stylus pens. And if you look at, let me highlight again, right here, where the graph of the original function is concave down, notice the blue is all below the x-axis. That blue is all down here. So where the original function is concave down, f double prime is going to be negative. So if f double prime is less than 0, then f of x is concave down. All right. So what we're going to be doing is, just like we worked with the first derivative, we found critical numbers, did the number line, tested the intervals. We're doing that same thing today, but with the second derivative, if you will. Now, and I talked a little bit about this, where the purple and green meet, where a graph changes concavity, whether it's from concave up to concave down or vice versa, that point right there is called an inflection point. And I mentioned this in the activity last time, but that's called an inflection point. Jeez, oh Pete's. So an inflection point is a point on the actual function where a graph changes from concave up to concave down or vice versa. Okay, so it has to be an actual point on the function. So here's how we're going to be doing this. It says find test intervals by finding where, here's what we're going to be looking for. Just like when we found critical numbers, we're going to find where f double prime equals 0. So we're going to take the second derivative, set it equal to 0, kind of like we're finding critical numbers, but now we're talking about concavity. So set f double prime equal to 0 and solve. Anywhere f double prime is undefined, that's what we're going to set up on our number line. And also, anywhere f of x is discontinuous. This is how we set up our test intervals on the number line. Same exact way we evaluated increasing and decreasing, where we would set f prime equal to 0, find where it doesn't exist, find any sort of discontinuities like vertical asymptotes in the original function, we would set up our intervals. We're doing the same exact thing today, but with double prime to look at concavity. All right? So, let's go to first example. It says, determine the open intervals on which f of x is concave up or concave down. Also locate any inflection points. Okay. So what we need to do is find f double prime. So first find f prime. F prime is 4x cubed minus 12x. F double prime is 12x squared minus 12. So what we're after is anywhere the second derivative is 0 or undefined, or anywhere the original function is discontinuous. So we set this equal to 0 and solve. So factor out of 12. Factor x squared minus 1. So x equals plus or minus 1. Now what these are not critical numbers. Critical numbers only come from the first derivative. But these are called possible inflection points. These are the two places where the graph could change from concave up to concave down or vice versa. We call these pips. Pips. These are not inflection points yet, but they are possible inflection points. Just like when we found critical numbers, that didn't mean there was going to be a relative max there, but we had to test the intervals and see if the sign changed. Same idea. So these are pips. So now what we need to do, and again, pips are possible inflection points. What we need to do is set up our number line. And we're going to put -1 and 1, our test intervals. And this time we're testing f double prime on the number line. It's the same idea, but we're testing f double prime for concavity. So we are going to take a number in each interval, to the left of -1, between -1 and 1, and to the right of 1, and plug them into the second derivative. So if I plug a number less than -1 into the second derivative, so let's plug -2 into the second derivative. So we could plug a -2 in here to get the best idea. So if I plug -2 in there, we're going to get 12 times -1, so 12 times a negative, times another negative is a positive. So the graph in this interval is concave up. If you plug 0 into the second derivative, you get 0 minus 1, -1 times 12 is negative. So concave down. And if you plug 2 in, you're going to get positive, positive, positive. So concave up. All right, so let's answer the question now. It says, determine the open intervals on which the function is concave up or concave down. So anywhere you have that U shape, it's concave up. So we would say, let's see, f of x is concave up on, and so let's see, it's everywhere from -infinity to -1, union 1 to infinity. And it's concave down between -1 and 1. So -1 to 1. It also says locate any inflection points. So that's where the graph, that's where f double prime will change from positive to negative or negative to positive. So if you look here, f double prime changes from positive to negative at -1 and at 1. And so we say inflection points. at x equals plus or minus 1. There you go. So again, it's the same idea. You just have to know now you're going into the second derivative and that test for concavity. All right. Example 2, determine the open intervals on which f of x is concave up or down. Also locate any inflection points. So anytime I see the word concavity, I think second derivative. So let's do it. F prime is 4x cubed. F double prime is 12x squared. And we're after anywhere where this is 0 or undefined, or where the original function doesn't exist. So set this equal to 0. So x equals 0 is a pip, possible inflection point. Okay, so now we set up our number line. Plug 0 in, and we are testing the second derivative for concavity. So if I plug a negative in to the second derivative, a negative squared is a positive, so it's positive. So concave up. And if I plug 1 in, I also get a positive. Concave up. So it's concave up everywhere. So we would say concave up, f of x is concave up on the interval negative infinity to infinity. And since it didn't change concavity at all, no inflection points. All right. So just like we had a first derivative test, we also have a second derivative test. Okay, so here's the second derivative test. And this is going to help you find any sort of relative extrema, just like the first derivative test does, but it works a little different. Here's how. It says, let f be a function such that f prime of c is 0. So the derivative at a point is 0. So there's some sort of hump, whether it's a relative max or relative min. And the second derivative of f exists on an open interval containing c. So here's the second derivative test. If the second derivative is positive, and so understand you have to put these two things together. If c is an x value where the first derivative is 0, and f double prime is positive. So think about putting these two things together. You have some sort of either, you don't need to write this, but you either have something like this or this, if the first derivative is 0, so it's either here or here. And if the second derivative is positive, then you have concave up. So if the first derivative is 0 and the second derivative is positive, then you know that whatever that c value is a relative minimum. So it's kind of putting those two things together. If you have, like I said, a c value where the first derivative is 0 and the second derivative is positive, so concave up, then you know you have a relative minimum there. So to write this into, oh shoot, to put this, why won't you erase that? Gosh dang. I feel technologically idiotic. You won't erase. Well, phooey. I'll just write over it. In blue. So if f double prime is greater than 0, then f has a relative min. At c, comma, f of c. But again, you have to put these two things together. So it's, you find where the derivative is 0, and I'll show you how this works here in a second. And if the second derivative at that x value is positive, then it's a relative min. And if you find a point where the first derivative is 0 and f double prime is less than 0 at that x value, so that would mean concave down, then f has a relative maximum. At c, comma, f of c. And if you plug that c value into the second derivative and it equals 0, then the test fails. You can't make any conclusions. It could be a relative min, could be a relative max, or it could be neither. So this test could fail, in which case then you would have to go to the first derivative test and test your intervals and look at it in that regard. Okay, let's look at what this looks like. Let's do an example of this and put it into context. So it says find the relative extrema for f of x. Okay, so we could use the first derivative test that we know how to do, or we can use the second derivative test. Let's see how it looks. So first find f prime. F prime equals negative 15 x to the fourth plus 15 x squared. And we need to figure out where this first derivative equals 0. That's the first part of the second derivative test. Figure out where this equals 0. Notice it says equals 0, and we're not finding critical numbers. We're not finding where it's also undefined. Well, we're just after where it equals 0. Where does it have a nice smooth hump? So set this equal to 0. And factor. So factor out negative 15x squared. And then you get x squared minus 1. So negative 15x squared, x plus 1, x minus 1. So x equals 0, plus or minus 1. Here's what we do with these. These are possible locations of relative maxes and mins. We've talked about that for a couple lessons. Here's how we use the second derivative test. Find the second derivative. So we're going to get negative 60 x cubed plus 30x. And what we are going to do is take these three x values that we found and plug them in to the second derivative. We're going to plug them in and see if we get a positive number, a negative number, or 0, and then use the second derivative test. And here's what this looks like. Let's plug those three x values into the function, f double prime. So if I plug 0 in, f double prime of 0, if I plug 0 in for the x's, we get 0. So if you look back at the second derivative test, if it equals 0, then the test fails. We can't make any conclusion from that right there. No conclusions. Test fails. But if we plug f double prime, if we plug 1 in, then we're going to get negative 60 plus 30. So we get negative 30. The number doesn't matter. What matters is that is less than 0. What that means is this, at this point, the graph of the original function, since it's negative, is concave down. Looks like this. So since 1 is a place where the derivative is 0, and it's also at a place in an interval where a graph is concave down, then you can conclude that at x equals 1 is a relative maximum. So that's how we're using the second derivative test. So, and we can figure out what the y value is by plugging 1 into the original function. What that means is, so 1 comma 2 is a relative max using that second derivative test. Then plug in f double prime, plug negative 1 in. If you plug negative 1 in, you get 60 minus 30, you get 30, which is greater than 0. It's positive. So negative 1 is in an interval that's concave up. So that means you have a relative minimum. So negative 1, negative 2 is a relative min. That's how you use the second derivative test. And the AP exam will find, well, you could say, well, why don't we just do what we did before and just use the first derivative test? Well, the AP writers and people who make the test are going to force you to know how to use the second derivative test. They'll give you limited information about these values so that you have to understand how to apply it. Like they might tell you f double prime of 1. They might say f prime of 1 equals 0 and f double prime of 1 is negative 30. So is x equal 1 a relative min or relative max? They might not give you a function, so you have to know how to apply this, okay? And you'll get more practice with that in your assignment. So in conclusion, with the second derivative, if f double prime is positive, then f is concave up, and understand what it means to be concave up. That means f prime is increasing. That means the slopes are getting bigger, like I showed you at the very beginning of the lesson. And if f double prime is less than 0, f is concave down. And that also means that f prime is decreasing. So the slopes are getting smaller. Good luck.